Today, we want to get our last bit about differential equations, maybe until I think of something else that's also shiny and interesting. We looked at second order linear homogeneous ordinary differential equations with constant coefficients, which really is just like y double prime plus by prime plus cy equals 0, where b and c are constants. The second order refers to the second derivative. That's the highest order derivative that we have. The linear parts means the derivative and the function y prime, and y double prime are all to the first power. The homogeneous part is the equal 0. The ordinary part is the fact that we're using ordinary derivatives and not partial derivatives. And the constant coefficients is because we got a 1, a b, and a c. Those are constant coefficients. If you're looking for the more general version where you have a y double prime, just divide by a, and then that's the new b and c. So that won't change anything. The strategy that we employed was the tried and true guess and check method. So we guessed that y equals e to the kt is going to be the solution that we want. And that makes sense because we're looking for a function whose derivatives are all like terms. The function, the first derivative, and the second derivative, we've got to be able to add these things up and come up with 0. That means they need to be all like terms. So we guessed y equals e to the kt because the derivative will just be a constant times e to the kt. And the second derivative is also some other constant times e to the kt. Plugging that into the equation led to the characteristic polynomial, or the characteristic equation. I had to tack on the equation part because I've been solving equations in algebra class, so I've been equaling 0 a lot. So k squared plus bk plus c is the characteristic polynomial, and equals 0 is the characteristic equation. Since the second order equation has led to this quadratic equation, we know there are 3 things that can happen. We could have distinct real zeros. So the 3 things that can happen. We can get distinct real zeros. I'm going to write solutions since I wrote the equation. Distinct real solutions, I could have a repeated solution, repeated real solution. And we could have complex conjugate solutions. These are the 3 things that can happen when we're solving a quadratic equation. We can have 2 x-intercepts, 1 x-intercept, or no x-intercepts. So it's all connected. When we get distinct real solutions, we get a general solution that's just e to the k1t and e to the k2t. So that's no problem. The thing that we have to remember is that the general solution of a second order equation needs to have 2 linearly independent solutions. That, I think I said general solution already. So the other thing that we have to concern ourselves with is that the general solution to a second order differential equation needs 2 linearly independent solutions. I just stated this yesterday. I didn't justify it. I just said there has to be 2. This is not a problem if we have distinct real solutions. Because if I have 2 solutions to the characteristic equation, K1 and K2, e to the K1t and e to the K2t. We just make a general linear combination of those two. So the example you saw yesterday was y double prime plus 2y prime minus 15y equals 0. Our characteristic polynomial was k squared plus 2k minus 15. And so the zeros of the characteristic polynomial were 3. I think I did it the other way yesterday, but I also wrote y instead of k. We get those two distinct solutions. K is 3 and -5. So we got distinct real solutions. Our general solution is C1 e to the 3t plus C2 e to the -5t. The C1 and the C2 are arbitrary constants. E to the 3t and e to the -5t are our linearly independent solutions to our differential equation. So any solution of this differential equation must have this form. It's some combination of e to the 3t and e to the -5t. And we found this out by doing the super technical thing we guessed. So all right. So let's take a look at this second order equation. We got y double prime minus 6y prime plus 9y. We're going to do the same thing. We guess that y equals e to the kt. That's going to lead to the characteristic polynomial. The e to the kt we can factor out. And so the characteristic polynomial is what's going to determine what will make this 0. And so we just go right to our characteristic equation. K squared minus 6k plus 9 equals 0. And now we see why this one is different. Because this is a square polynomial. So in this case, we don't get two distinct real solutions. We get a solution that appears twice. A second degree polynomial always has two complex zeros. So a quadratic equation will always have two solutions. It's just that sometimes one of the solutions gets repeated. So the 3 counts twice because it was a k minus 3 squared. That's an important piece of information. But we can't make distinct we can't make linearly independent solutions to the second order equation with just an e to the 3t. I can't have an e to the 3t and another e to the 3t because they're not linearly independent. So if I try to write a solution with a c1 e to the 3t and a c2, leave a space, e to the 3t. These are not actually different. E to the 3t and e to the 3t are just multiples of each other. And we should just add those two things together. But we need two linearly independent solutions. So there's no trick to it. It's just a simple trick. If I multiply e to the 3t by t, I still have a solution to this differential equation, and it is no longer a constant multiple of just e to the 3t. So there's no trick to it. It's just a simple trick. Now I need to verify that this is actually going to be a solution to this equation. We know that e to the 3t is going to be a solution to this equation because that's where this whole thing came from. So let's just focus on this t e to the 3t and verify that t e to the 3t is also a solution to the equation. So if we get this, if this term actually works, then we have another solution to this differential equation. So let's see if that works. So my differential equation is y double prime minus 6y prime plus 9y equals 0. And my proposed solution is t e to the 3t. In this case, when we go to check, we're going to have to make sure we use the product rule. So y prime will be the derivative of the first times the second plus the first times the derivative of the second. And our second derivative, I need just the chain rule for the first term, but I'll need the product rule for the second term. So y double prime will be a 3e to the 3t plus the derivative of the first times the second plus the first times the derivative of the second. And so now we can see how things are going to start canceling out, because in the second derivative is where I pick up a 6e to the 3t plus a 9t e to the 3t. So let's drop all this into our differential equation. So y double prime is 6e to the 3t plus 9t e to the 3t from the differential equation is a -6. And y prime is e to the 3t plus 3t e to the 3t plus 9 from the equation. And y is t e to the 3t. From the equation, we're trying to verify that this is equal to 0. So that means the e to the 3t terms need to cancel out, and the t e to the 3t terms need to cancel out. So what we've got is 6e to the 3t plus 9t e to the 3t minus 6e to the 3t minus an 18 t e to the 3t plus 9t e to the 3t. So the 6e to the 3t and the negative 6e to the 3t, those drop out. And then the two 9s combine with the negative 18, so everything drops out. This raises an interesting question. Could we have dropped some t's on our other one? What if instead of e to the 3t, we used t e to the 3t? To which the answer is, good question. Moving on. That's my way of saying, that's a good question. You should check. Although I will observe, if in fact t e to the 3t would work in this y double prime plus 2y prime minus 15y equals 0, that raises the question, is why didn't we use that? And the answer is kind of, well, e to the 3t works, and that's simpler to work with. But that should start making us suspicious. But it should lend some justification for why we're going to have a rule, like not necessarily a rule. We're going to have to say something like, well, we need 2 linearly independent solutions. It's not enough to just have e to the 3t. We need something else. So this is something that maybe you should check out. Then if it does, why does this happen? And if it doesn't, then that brings us back to, why does this work so well in the repeated roots case? So that's something for you to check. So what about complex conjugates? What if we have a second order equation that leads to a quadratic polynomial with complex conjugates for zeros? So I recommend starting off with the easiest case, pure imaginary ones. So y double prime plus 9y equals 0. So let's combine the things that we know. Let's examine this by combining the things that we know. We know that the characteristic equation will be k squared plus 9 equals 0. And so our solutions will be complex conjugates 0 plus or minus 3i. This leads us to a problem. What's e to the 3i times t? Can we just drop a complex number in there? Not really. We don't want complex. We don't want to have functions of complex numbers like this. This is supposed to be, we're supposed to be keeping it real here in single variable calculus. So let's come at this from another angle. Let's take a look at what we have. We've got y double prime plus 9y equals 0. In this case, I need the function and its second derivative, just its second derivative, to be like terms. I need the function and its second derivative to be like terms. We need y and y double prime to be like terms. I needed e to the kt for to get y prime and y double prime to all be the same. But now I can skip the y prime for this one. I need y and y double prime to be like terms. So that gives us two possibilities. If y is the sine of 3t, if y is the sine of 3t, then y prime is going to be 3 times the cosine of 3t. And y double prime will be negative 9 sine of 3t. So here's why we can pick these trig functions. Here's why we can pick these, picking these trig functions is a good choice for this particular equation. The second derivative and the original function are like terms. The cosine, we are skipping in the equation. So I just need the y and the negative 9, the y equals sine of 3t and the negative 9 sine of 3t. Those will cancel out in the equation. Negative 9, y double prime is negative 9 sine of 3t. The equation has a plus 9 in it. And y itself is sine of 3t. And so this satisfies the equation. This is all equal to 0. But just like Skywalker's, there is another. But original trilogy, there's only two. There's nothing to stop us from starting off with cosine of 3t, so that the first derivative is a negative sine. And the second derivative is back to being a cosine. Here, if we check this into in our differential equation, I have negative 9 cosine of 3t plus 9 times the cosine of 3t, which was what we started with. Add those up and we get 0, so these two satisfy the equation. We've got now two linearly independent, because sine is not a multiple of cosine. We've got two linearly independent solutions to the differential equation. We can combine them into a general solution. So if we get solutions that are pure imaginary, it looks like we're just going to have trig functions, sine and cosine. This raises more questions because we should always just be raising more questions. I think some people get the wrong impression that teachers' job is to like answer questions, and that's just not it at all. I don't know if you've noticed the pattern. The only time I'm answering a question is when it just leads to more questions. If I answer one question and it makes 3 questions that you now have to answer, then it's a question that I'll answer. But if I'm going to answer a question and it's just going to stop the whole conversation, then no, I ain't answering that question. You know what I mean? I think I've mentioned it before in this class. When you graduate, if you don't have more questions when you graduate college than you had when you started college, you did college wrong. You're viewing college as a place to apparently learn skills and get knowledge. But college should be a place where you get knowledge that only leads to the desire for more knowledge. So if you walk out with more questions and the desire to go forth and answer those questions, then college worked. If all you want to do is get a good paying job, then you probably should have just done that. I mean, not that there are good paying jobs, but I don't know if that's going to be a thing anymore. Because we've all accepted that working 120 hours a week is acceptable. Our corporate overlords have deemed that our lives are only worthy of the labor that we can produce and the money that we can make for them. So, or we could not buy into that. So I answered this question, what the general solution of y double prime plus 9y equals 0. It's a very niche question to ask. I guess y double prime plus some constant times y, I've taken care of that one. But this raises some more questions. What does e to the 3it have to do with sine and cosine of 3t? Lots of questions here. Oops, 3it. What's e to the 3it have to do with sine of 3t and cosine of 3t? Why did that happen? Also, you notice that I picked an equation that has pure imaginary solutions. What if the equation has complex solutions? What if it was e to the 2 plus 3it? What is that e squared going to get us? So for example, what if we had y double prime? I need a 4 and a 13. I put plus 2, so minus 4y prime plus 13y equals 0. If I drop in this minus 4y prime, all of a sudden my solutions are going to be 2 plus or minus 3i. Where's that 2 going to show up in my general solution? No longer pure imaginary here. So if I just answer these questions now, then all of calculus will snap into focus and everything will make sense. And your mathematical lives will be easier all the way through graduate school, just by answering this one question right now. If I wait any longer to answer what happens if we have e to the 2 plus 3it, then you're just going to have to continue to work like you've always worked on math, and it won't be automatically made simple. Once again, if I just answer this question now and not wait to answer this question, then everything will magically snap into place. This is the final step, the final question to make the spell work. And we can just Gandalf this whole thing. So unfortunately, we're out of time and I won't be able to answer this question right now. So that's going to do it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing.